That's
Cool.
It's not wrong.
So, ready to begin?
Yeah.
yeah, I think so.
I think we are ready.
Okay, so, we got a binary tree here. Let's go through the ways you can traverse the tree. So, level order is, in my opinion, the most intuitive because you just go literally by vertical levels. So, in this case, you traverse it in order Q, A, K, D, J, E, F. D, J, E, F, G, H, I. You're going through, like, scanning. You're scanning a
Wait, what
document.
happened?
I moved it down so you can actually point to it.
Oh, okay.
Like,
Hold on.
Yeah, basically level by level.
Yeah, as if scanning. Oh, it's getting a
There's like an empty space, there's no H there.
So it says Q and then like you just go like this, basically? Right?
Yes.
Yeah, okay.
Yeah, there's nothing here, but that's fine. You just skip over that. There's nothing to traverse there. You just move on. So G, H, I.
Are you guys recording?
Yes.
Yes.
Cool.
Pre-order. Let me look at my notes because I don't know the other three.
It's like,
Actually, does anybody,
Yeah,
Just
it's
go
pre-order,
right
in
now.
order, and post order.
anybody happen to have a USB-C cable on them?
yes, I do, very short,
Could I use it to charge my phone from my laptop so it doesn't die?
very short, that cable to be heard.
That's okay.
Okay. So this one, you're kind of sticking to the left as much as you can, and then when you go back up, you got to go all the way left again. So it'd be like G. Wait, is it G?
For pre-order?
No, it's Q A D G. Okay. So you go Q A D G J H I K E F. Make sure I didn't fuck
We're allowed
Is
notes
this-
for the test, right?
up. Probably.
Yes. Is this for pre-order?
Yes.
Yeah.
Yeah.
Can we write that down somewhere?
So,
I've been writing these down.
QAK,
Q
how about I lift up the screen and then we can just write it
Q
whiteboard?
A D
The actual letters aren't as aren't the actual letters
I K.
aren't as important as understanding the process of how this works. Oh God.
Yeah, well, I don't know if this is better or not.
Why is the Shadow the Hedgehog beautiful?
Don't worry about it,
What?
don't worry
These
about
were
it.
here when I got here, I didn't do it.
D G
Okay, so,
So pre-order, pre-order, you're traversing down, but as you're traversing down, you traverse or you visit every node on the way. So first you go left. Q, traverse left. A, traverse left. D, traverse left. G. Then go back up since this has no children. Visit the right child, nothing. Visit the right child, visit J, H, I. Go back up. Visit right branch, K, E, F. So the pattern,
It's
Worst pen of
outlining
all time.
going to the left.
what?
It's outlining the shape going counterclockwise.
Yes. Yeah, that's how it goes. You're right.
Yeah, basically, essentially you just visit first and then traverse.
Yes. In order. Let's see. Good,
So, for pre, in, and post order, essentially when you traverse the entire tree in depth first order, you're going to be visiting each node 3 times. The first time you visit it, so when you come down from Q to A, then when you come back from here, from D back to A, and then when you come back from J to A. There are 3 visits to each node. And the difference between each of these traversal orders is which one you visit the node on. So pre-order, you do whatever operation, you visit it on the first time you see it. In order is when you come back from the left side, and post order is when you come back from the right side.
That sounds about right.
And the reason for that is because, or the reason it's called in order is because it's in between.
So post order would be, G, D, H, I, J, A.
So post order is first,
E, F, K, Q.
first you
Yes.
visit right, then you visit left, then you traverse.
Yes.
So when you're visiting left, you go, all right, not traversing it because I gotta go left, not traversing it because I gotta go left. All right, traverse left, traverse right, visit,
And this is-
nothing, visit,
This is post order?
I think so.
Yeah.
We're not
H.
going in order, I guess, that's fine.
HI, visit, visit.
H, I, J?
So it just depends on which place in the sequence of 3 you place the V for visit.
I'll just read off
The
the,
whiteboard isn't being streamed.
God?
Oh, that's true. The whiteboard is not being streamed. The
That is
screen
so
is.
true.
I'll just read off the answers to make this simple.
That's why I was, yeah, I'm writing them down at the moment, but it's a little hard.
Pre-order. Q, A, D, G, J, H, I, K, E, F. In order. G, D, A, H, J, I, Q, E, Q, E, K, F.
Q, E.
Post order. G, D, H, I, J, A, E, F, Q. Fuck. G, D, H, I, J, A, E, F, K, Q.
Should we
I'm
turn on
so
the
sorry,
camera
but
then?
could you read in order
the-
again?
Let's see if I can do that.
You wrote it down?
Yeah.
Okay, never mind.
GBA,
Oh,
GBA.
GDA,
Game Boy Advance.
HJI, Q,
Oh, yeah, I
E,
would turn
K,
the,
F.
you can test it and see if it works,
how strange.
because it's always wonky with the. It might not work.
I love taking
It
notes.
might be wonky.
No?
Oh,
Yeah,
boy.
Yeah, that works.
That works
Okay.
pretty good.
Yeah.
Eh?
Yeah, you're gonna have to take it off of Discord, yeah.
I feel like I'm looking into the matrix.
I'm glad somebody else is writing these, because I definitely did not get all of those, but that's fine.
Yeah.
I will share my notes afterwards.
Okay.
I see.
I've also got some notes written down.
I'm taking them in a nice digital format, so,
Come on, man.
be easy to share.
Called the market.
Writing things down on paper helps you remember better.
But I'm writing down, I'm using my pen.
It's not the same.
And then in order is.
You're just
left,
biased.
Is it right?
I'm not biased, I've taken a psychology course.
So there's.
Psychology is biased.
Did the
This
psychology
is
course
right.
bias you?
Visit right.
Why is it, why is this?
And left.
Why does Edge not go fucking
Yes.
full screen anymore? It was doing fucking big hill. Fuck.
Alright.
Wait, can you quick go over in and post order again?
Yes. So for in order, it's you can think of it as if this was a sorted tree, like a binary search tree. You'd be visiting them in sorted order. So it means that you visit once, visit once, visit once, visit once. Then this one you would visit its non-existent children, but after the first one you would visit it for a second time. And if you're in order traversal, that means that's when you actually visit it. And so you would mark down G. Then you come back to D. This is the second time you've seen D, so you would mark down D. Then you would go back, you would go to A. Second time you've seen A, so you'd mark down A. Then you go to J, then H, then back to J. Or sorry, you would mark down H because you visited its non-existent children. Back to J. J is second time you've seen it, so you mark it down. Same with I. Then you go back up. Third time you've seen J, so you don't care. Third time you've seen A, so you don't care. Second time you've seen Q, so you mark it down. Then you go to K, E, mark down E. Then you go back to K, mark down K, F. And then you go back up to K, third time you've seen K, back up to Q, third time you've seen Q. And once you've seen the root for the third time, the last time, then you're done.
Okay.
Post order is the same except you do it on the third visit. So you go all the way down here, then G, one visit, 2 visits, and then back to 3 visits, mark down G, then D, because you came back from G, then went down, then came back to D, then A, you go down to J, then you mark down H, I, J, because you're coming back, A, because you're coming back, go back up over here, K, go down to E, mark down F, then go back to K for the last time, mark down K, and then Q is the last one.
Okay, so the difference is you visit both as children first.
Exactly.
Okay.
Yep. So, yeah?
Would it be accurate to say that in order traversal is the same as ascending value?
Yes.
Order?
If the tree is a sorted tree, like a binary search
Yeah,
tree.
it's fine.
Yes.
If it's not sorted, then it's just in a different order.
If not
Exactly.
sorted, how the fuck do you traverse, how do you like navigate it?
What?
If it's not sorted, how the fuck do you navigate it?
Just by
You
using
just-
left
using-
and right.
You
just
can
block
use
it.
the children pointers. As long as you don't care the order that the values are actually in.
Yeah, it's a
then
lot quicker
okay.
when it's sorted, but when it's not sorted.
So like, the concise way is that pre-order is visit, then go left, then go right. In is go left, then visit, then go right. Post is go left, then go right, then visit.
Oh my god, 3 visits.
Yes.
Oh.
3 visits for any type, because you're gonna come down once and then come back from each child. All right. Any more questions?
Do we go over level order?
Yes.
Oh, yeah.
You just scan it.
So
Scan it.
wait, level order is like breadth first search?
Oh, okay, cool.
Like
Is that what
reading
it
the
is?
book.
Yeah, it's
Okay.
like a zigzag Z.
Okay, so it'll just be Q, A, K, D, J, E, F, G, H, I.
Yeah.
Okay.
Cool.
Which one do you want to use for printing?
Very few of those letters are on this tree.
Basically the same as a breadth first search.
This is a random series of letters.
Yeah.
Not sorted.
It is, yeah, it's not sorted, but it never says binary search tree, so it's fine.
Yeah. It's just a tree.
I love
I love refrigerators.
I love refrigerating.
Pretty sure that guy's from Florida. He's
I
from my area.
Would not be surprised.
All right.
We picked against this earlier, but it's okay. That was just a.
What is the maximum number of nodes in a tree with branching factor 2 and height h?
Oh, this is simple. All right.
Here we have a tree with a branching factor 2 and a height h. How many nodes does it have maximum?
Is it 2 to the power H?
No.
No.
Almost, but not quite.
The sum of 2 to the power H.
No.
Starting at, or 2 to the power n equals 0.
It's
from
not
n
an
to H.
integral either.
No, it's not integral, it's a sum.
It's that.
Okay, so,
You motherfucker, that's just the geometric sum.
Yes.
oh, maybe it is. H, not n. Sorry, I didn't make the tail tall enough. 2 to the power h plus 1 minus 1.
Does this hold true for any branching factor?
No.
No. If it were 3, it would probably be 3 to the h plus 1 minus 1, by my guess.
Well, yeah, I mean, that's what I mean, is it
Is it like
for any
factor?
branching factor n, is it n to the power of h plus 1 minus 1?
I think so.
Probably.
Let's check it out, shall
Factor
we?
of branching. Let's try it. So, yeah. As you can see from here, height 0 is the single node with no children. That's why it's plus 1, because it's 0 indexed.
9, 9, 9, plus 9, plus 4.
You can kind of think of it as like similar to the number of numbers that can be stored in that amount of bits.
I prefer the number 2 anyway. I don't like 3. Cool. Maximum number of nodes on the last level of the.
So easy way to remember it is just draw a diagram with three levels. That's height 2, and count how many there are. It's 8. That's 2 to the third minus 1.
that last one has 4 nodes on the bottom, on level
4
2,
plus 2.
so that's 2 to the h. The 2 to the 1, or actually no, 2 to the something minus 1, that's just the rest of them.
Any questions?
Branching factor is just how many nodes, or how many children a node has, right?
Yep.
Okay.
Exactly.
Cool. Approximately, it's about 1 to 1.
What is the maximum number of nodes on the last level in a tree with branching factor 2 and height h?
Well, if h is 2, then the tree has 7 nodes, and the last level has 4 nodes. So that's a ratio of 4 to 3. As you tend toward infinity, this ratio gets very, very close to 1 over 1. So it's about equal, except the denominator is just, no, the ratio is 1 to 1.
No, for this question.
Oh, for that one?
What's the maximum number of nodes on the
2
last
to the
level?
h.
Wouldn't,
Isn't it like n2 and minus 1?
No, that was for the one before.
These are 2 different questions.
I
One-
know, for the,
Oh. Sorry?
which one are we on?
This one.
Okay.
Last
I'll go
last
back.
level in a tree. So the last level will have 2 to the h nodes. Because 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. Because you're multiplying by 2 every time, obviously.
Yeah. Cool. Ratio, about 1 to 1.
Yes.
Is it not n2?
Nope, it's just 1 to 1. Because if you have 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 1, 2, 1. All this is 7. All this is 8.
Yeah.
Then you'll get to like 64 and 63. Actually, no, it's the other way around. 64 to 63.
And that ratio tends to
2048 to 2047. So it's about 1.
So in the previous formula, the +1 is to account for the rest of the levels that aren't the last level?
Yes. Sorry, in which previous question? Number 2?
H plus n to the power of h plus 1 minus 1.
Yeah, so that's because height 0, you still have 1 node. And so like height 0 is 1 node, that's the root, and then height 1 is with a level with 2 nodes. So you have to go up by 1 to the power of 2 to account for that upper level. Because it's 0 indexed instead of 1 indexed for height.
What was the answer for the one above that?
What?
Yeah, well,
What's the maximum node in the last level tree? 2.
and this one is 1 to 1 because it wants the approximate ratio without a specified h. So it's not a powers of 2 formula. Cool. Any questions? Cool. Next section. Answer the following questions using words rather than code. How do you find the smallest element in a binary search tree?
We'll go left.
Well, left,
Start
assuming
at
it's
the root
sorted.
and keep going.
It's sorted. You can assume it's sorted.
If
because
it's
it
a
says
binary search tree,
Oh,
it
yeah.
means it has to be sorted.
Well, mine sure aren't.
That is unfortunate.
I'm joking, I haven't had it.
Just go all the way left. Cool. Explain how to find the successor of a given node in a binary search tree. Anyone know this one?
On the rightmost child of his parent.
It's
Not always.
It's a bit complicated, right?
There's a bit more to it than that.
Yes. If your node has a right subtree, then you find the minimum index right subtree, so that's a successor. But if it doesn't have a right subtree, then you have to go up your parents until you find the first ancestor that's the left child of its parent. then that, and the ancestor above that is the minimum, or the successor.
It's a left child, right?
Yes.
Yeah. So so what this is saying is that if you have a tree like this, and they're connected like that, so the successor of, I guess, of this one is going to be, it has a right subtree, so you're gonna find the minimum of the right subtree, which means you go down here, and then you go to the left, all the way down. As if there were more, you keep going. And that means this is the successor of the root. If there's no right subtree, such as this one here, then you go up until you find, I guess this is not a left child, but the root.
It's right as in left child.
Wait, what? Oh, right.
This thing's right has a left
As
child.
a left child. No, but this would be the successor. Oh, it's 5, 4,
6, 5.
oh, wait.
7,
I remember
5,
that.
6, 4.
It's nearest ancestor that you
So if
traveled to the left to get from.
Yeah.
Right, okay, so not its ancestor that is a left child, but that.
Yeah, so it's
That
weird, because you have to
came
go
from
up
the
the
right
parent
of?
pointers until you find an ancestor who, in its parent, is the left subtree. And that parent above it is the successor.
Trying to figure out a good way to word this. Sorry, can you repeat that for me?
Yeah, so, though if you don't have a right subtree,
Mhm.
then you go up the parent pointer until you find an ancestor in its ancestor, it is the left subtree. That ancestor is the successor.
But what about the root?
Uh,
The root doesn't have an ancestor.
Then you'd stop if you didn't find one. So if you went so for example, 10, right?
Yeah.
10 doesn't have a right subtree. So,
But what about for 6?
well, yes,
Seven should be.
7's the successor, so you start here.
Yeah.
And you go left, and you're like, okay, well, I'm the right subchild, so clearly I'm not the successor.
Right.
But 5 is the left subtree of 7.
Mhm.
So 7 is the successor.
I see. So you find the parent of the first parent of the parent of the ancestor of this that is the left child.
Yeah.
I see.
It's really weird. And the same logic applies if you're also finding the predecessor. But just, instead of the left subtree, instead of being the left subtree, it's the ancestor above the, yeah, it's hard to put into words very concisely.
And the successor is that node's parent. Okay, so what this means is, like you said, you find the first ancestor of the node you're looking at that is a left child, because every node is either a left child or a right child. This is a left child because you go left to get to it. This is a right child because you go right to get to it. So to find the successor of 6, you go up until you find a parent that is a left child, which in this case is 5, and then you use its parent as the successor, which is 7. So if there were more nodes down here, then to find the successor of this one, you would go up until you find a parent that is, an ancestor that is a left child, so that would be this one because it's a left child with 6, and then you would use its parent as the successor, which would be 6. This one it would be you go until you find one that is, oh wait, hold on.
Yeah, then the successor is the
We're
its
also-
parent, right?
We're also neglecting
The
the one
roots.
case of if the node of the successor you're trying to find is a left subtree, then you need to go to the right subtree of its parent to find the node.
If it's a left child, then it's just its
Oh, then its
parent.
parent is just a successor.
Yeah.
Okay.
Right.
You start at the node, so you have to start at the node that you're like, so yeah, in that case, you have to start at the node itself and then check to see if it is a left child, then the successor is its parent.
Right.
But the oh, I see, yeah. So nearest ancestor, including itself,
Yeah.
that, okay. Okay, so that covers this case where you say, what's the parent, or what's the successor of this? Well, this is the first ancestor that's a left child is itself, if we're including itself as an ancestor, so its parent is the successor. If there is no right subtree and there are no parents of it that are left parent, or that are left children, then it means it is the last one and there is no successor, because it is already the maximum of the tree. Okay, that covers all the cases of if there is a right subtree, if there is no right subtree, and if it's the last one.
Is the next question gonna be predecessor?
If it is, we know how to do it.
No, it's how to delete a given node.
Oh boy.
All right. Let's do the table. All right. Let's say 6 doesn't exist. Uh-oh. Oh, actually, that's not the deletion. I'm deleting 5. Cool. So that I can handle having a child and having a not child. All right, so 5.
Hold on.
Yep.
You deleted it.
Oh, I thought you said hold on.
Oh, no, I said all done.
Oh, actually, no, I shouldn't have to have a child. All right, so, and you should have 3 and 4. There we go. 5 is gone. So, 4, because,
Actually, how do I explain this back?
I don't know.
Isn't there a note for this on this website? I wish I wasn't using my laptop to.
Yeah.
I think I know. Okay.
So 4 gets promoted, yippee, 3 gets promoted, yippee.
For what?
Well, hold on, that's the case in which the node you're deleting has 2 children, right?
Yes.
If it has no children, no problem. If it has 1 child, then boom, just promote that child.
But in 2 children, you have to do something slightly different, I believe.
Yes. You need to basically recursively promote all children under it.
Yes, so there's a couple of keys.
You probably do this with some kind of recursive function call because these have children, these
Yes.
have children, so you just gotta keep promoting children into adults. But the end goal is you should promote the left child over the right child. For some reason, I forget. That's that. Simple enough.
2 children, you promote a child,
Not necessarily.
and then you copy the value of the left child, and then delete the left, and then recursively delete the left child.
Something like that.
Okay, so yeah. If it is a leaf, that's trivial. If there is an empty child, then you promote. And if both children are, if there are both children, then, let's see, this says you can replace the data with the predecessor. I see. You can, oh, okay, I see. You can replace the deleted predecessor and then delete the predecessor.
I mean, this is fairly simple because it's just a binary search tree. If it were a balanced search tree, it'd be a whole other way to do this.
Yes.
I have it.
In words, what does one do?
Yes, so,
Yeah, delete it and replace it with left child.
If your node delete, then you can just delete it.
yep,
If you have one child, then you just promote the child to yourself.
Yes.
And then you just delete that child.
mhm,
Then, but if it has two, if it has two children, you have to find the successor.
mhm,
You have to take its contents and put them in yourself.
Yes.
And then you have to recursively delete that child.
mhm.
Okay.
There's also.
As in repeat the whole algorithm
Yeah,
of
repeat the-
checking if it has children and things
With
like
the
that.
successor, not the predecessor?
Either one will work, because you're guaranteed to have both children in that case, so you will have either a successor or predecessor,
Yeah.
so either one works.
Okay.
So yeah, to restate that again, it's leaf is trivial. If there's an empty child slot, then you can delete and promote the child that it does have. And then if both children are full, then you find either the successor or predecessor, replace the contents of that into the one you're deleting, and then delete the child recursively with that whole algorithm that I just stated.
I see. Because it can't keep having two children forever.
Exactly. Oh, wow, lots of space. Okay, given the tree below, calculate balances in all nodes. You may add balances to the picture above. Rotate left around Q, calculate balances in all nodes. Rotate right around Q, calculate balances in all nodes. Okay.
So should we assume that if they have a line but no node there, they only have one child?
Yep.
Okay.
So no-
As in, this is an empty connection.
Balance is just, what's that, just the size of this whole tree?
It's the difference between the size of the left and the size of the right tree. Or, sorry, the height. Is it height or size of tree?
Height.
I think it's height of tree, yeah.
What's the root balance of this?
The root balance would be the difference between the left and right subtrees, which we're calculating right now.
-1, right?
Wait, what?
Could you move for a second?
Wait.
Seth?
Okay.
It's
I see
height-
you're doing the balance. These numbers are the balances.
Yeah, I'm pretty sure Q has a balance of -1 though. This height, not number of nodes. In the right tree, it's the height of the nodes, not the number of nodes.
Mhm. So, height of this is 0, height of this is 1,
No,
height of
it's
this is
That
2.
was, yeah.
What?
Oh wait, height, okay.
Yes. Height of these are both 0, height of this is 1. So since height of this is 2 and height of this is 1, balance of this is -1 or +1, depending on your convention.
What's the
Left or-
balance of all nodes though?
Yes, so,
So G's balance is 0, D's is -1, A is -2, Q is -1, K is 0, E is 0, F is 0.
yes, so G balance is 0 because it doesn't have any children. This
Yeah, I
one,
didn't bother writing the zeros because they felt unnecessary.
so this one has one more height, because the height of this is technically -1, this is -1 if it's an empty tree. So, sorry, I'm not gonna write those because that's a height, not a balance. So the balance of this then is the difference between these, which is -1 or 1. Difference between these is, this one is 1, this one's -1, so difference is 2. This one is Each of these has a balance of 0 because no children, so they're equal, so the difference is 0. Difference between the heights of these is 1, so, or -1, depending on your convention of which side you consider heavier, being negative or positive.
Wait, so it's the difference of heights, not the difference of,
Yes, it's the difference of heights. So actually, okay, how about this? I'm gonna write both the heights and the balances to make it clearer. So this has a height of 0, this has a height of -1, this has a height of 1, 2, 3, this has a height of 0, 0, 1.
what does a height of -1 mean?
It means that it's an empty tree. Because we define a node with no children to be height 0, that means that if we have something with less height than that, it has to be, we define the height to be the height of its children plus 1. So if we want this to be 0, then the height of its children, which are empty trees, has to be -1.
Okay.
Is it not, it doesn't account for the other subtree? So I thought E and F would be height 1, since they're both at the same level as D.
No, it only depends on the local subtrees, not the parent subtrees. And then it's the maximum of the children's heights. So this one, the maximum of the children's heights is 2, plus 1 is 3. That's how we define height
Okay.
of a node.
And the balance.
And then balance is the difference between the heights. I'm gonna write the balance directly on the letter. So this one, difference of its children is 0 because they're both -1. This we don't actually define a balance for because it's not actually a node. This one has a height of 0 and a height of 0 and a height of -1, so its balance is 1. Then this one is a height of 1 and a height of -1, so its balance is 2. This one is 0 and 0, and its two heights are 0 and 0, so its balance is 0. And then height is 2 and 1, so its balance is -1. Or actually 1 in this case.
Do the negatives matter?
As long as you're consistent whether heavier on left or heavier on right means negative, then it's okay,
Okay.
but you can choose either one. So in this case, heavier on the left means positive balance, so there are no negatives because everything here is heavier on the left.
Okay.
Okay. Now I'm going to rotate left around Q.
That's pretty easy.
Yeah. So that means that our new root is going to be K. Wait, right? Is that right? Is it K or is it E? I don't remember.
I think it's,
I hate this class.
I think it'd be K.
Hit it on
I
Q.
think it would
Rotate
be.
left is to promote K.
Yeah, okay, yeah.
Hey,
Because you're rotating this entire tree counterclockwise.
Mhm.
So you need K and Q. So that means K is now above Q.
Cool. Okay. And then I'll redraw the tree after being rotated over here. So that would be K. And then on the left of K would be Q. And then basically.
Where does E go?
What? What?
Where's E go?
I haven't
get to
written it
that.
yet.
Okay.
And then off of Q, we still have A, D, G, and then, let's see, K. Yeah, no, K gets F, and Q gets E.
Right.
That way it stays in order. And now we can recalculate the balances again. So this is gonna be
A lot.
balance of 0, balance of 1, balance of 2, balance of 2 because it does have 1 here. This one will get a balance of 0. This one will get, let's see, sorry, so height of this is 0, height of this is 1, height of this is 2. Height of this is 0, height of this is 3. And difference between these heights is 2, sorry, yeah. Height of this is 1, height of this is 3, so this should be a balance of 2.
2?
Yes.
Alright.
So height of this here is 3, and height of this is 0. Oh, sorry.
Yeah.
Oh, sorry, yes, you were right, it is 3.
Isn't it negative to the left?
It depends on your convention.
Yeah.
So you either choose one and stick with it, basically. It's like a coordinate system.
I prefer to do absolute value in my case.
In this case, everything is balanced to the left, so you can just write them all as positive. If you have both, you should make sure that your rights are negative of your lefts. Those are all the balances for that. And now we will rotate the other way, which means A will become the root. If you want to redraw the arrows, you can. Which means that we can put now Q over here, and then K, E, F, and then over here we still have D and G. So balance of these two is 0 and 0. Balance of this one, its two subtrees are equal height, so it's 0. This one has a height of 1. This one has another subtree with a height of -1, so that's a balance mismatch of 2. This one is balance 0. This one is balance
1.
Yeah, so this is -2. Sorry, that's -2 and this is 1 if we're keeping the same convention, if left being heavier is positive. And then this has a height of 2, this has a height of 1, so -1 for the balance of A.
Wait, how do you calculate balance of A?
Balance of A is height of Q.
Wait, wouldn't Q have a balance of positive 2?
No, because its right subtree is heavier, and in this coordinate system, we're saying that's negative.
Left minus right.
Because
0 minus
all of
2.
all of these ones have been done so far with left being heavier is positive, so I'm keeping that consistent. You can write all of these inverted if you want,
Okay.
as long as they're all inverted. Can anybody tell me if this is an AVL tree, not including sorting, but if it's just balanced enough to be an AVL tree?
No.
No.
Why not?
Because D does not have a child. I
It's
guess
because
also
If it does not have a child,
a-
that's okay.
It's because of Q.
The Q is
Yeah.
Q.
Q has an absolute value of balance of greater than 1.
Yeah.
So it's not an AVL tree. Cool. Any questions? Cool. Next question.
What does AVL stand for?
It's the name of the guys who came up with it, their initials.
Yeah.
So
Some
they
Russian
have like
names or
Russian
something.
names I don't know how to pronounce.
Yeah, I think the L is in Landis.
There's two people and one of them has a hyphenated last name. That's why. There's 3 letters. Okay. Insert characters XRM or HRMXYI in this order into a hash using an array of size 7 and hashing function H of CH equals CH minus the character A mod 7 and linear probing. Extra copies are in case you mess up.
I like that.
Nice. And then we'll do the next ones after
Yeah,
that.
I have not learned hashing yet.
So hashing was one of the recent lectures.
I know.
I
So
love
we will
hashing.
teach you it very quickly. Hashing is where you're trying to map a set of possible values to a smaller set of possible values and hoping they don't overlap that much, and then dealing with it if they do. And that is used to efficiently store sets, like values from sets that can be very large, such as the set of all possible strings, or something like that, where you're not going to make a spot in an array for every possible string. So you pass it through a hashing function, which basically gives each string a sort of identifier, which in this case is a number based on the modulus of 7.
Is this like ciphers?
Kind of, yeah, it's kind of sort of a way of encrypting it into
Some
a smaller
ciphers
set.
use hash functions as encryptions.
Yes.
Interesting.
and then you store them in an array, and then you can look them up by hashing the value you're looking up, getting what's called a key, such as sort of like in a binary search tree has a key, or a heap has a key or whatever, to then go and find that value again.
So you're putting the value through the hash function to
To
get
store
its
it.
key, basically?
Yes, and then you store it at its key.
Right.
And then,
In the hashing function there, what is the minus prime?
oh, sorry, minus, it means minus the character A.
Yeah.
It's
Oh, okay.
That
it's
would be
like-
how you
it's
get
like
those
in
numbers
C++,
at the top.
I see.
the literal A is written
Yeah,
like that.
Yeah.
It just means that A is 0.
Gotcha,
As in,
it just wrote the
it means
weird.
this key is basically, so this is all the possible lowercase characters, and then these are their keys through that hashing function. Good job. So the way you actually do this is you say, pass it through the hashing function, which he's given a table up for us up here of the values and their keys after passing them through the hashing function. And then what you do with linear probing is a method of dealing with conflicts when two things have the same key, which in this case means any character with the same modulus of 7 value, so the same remainder when you divide it by 7, will have the same key, such as B and P, when you subtract A to get them indexed from 0 and then modulo by 7, will both give you the answer of 1, which means how do you store them both at the key of 1? You don't. You store, in this case, you would store B at 1, and then you would store P at the next available spot, which would be 2. Because it's linear probing, because it's
Goes up by 1.
linear time search to find it afterwards.
So you just insert it at the next available spot.
Exactly, you insert it at the next available spot. So,
Oh, but that
There's
does
also-
not mean, so because you're doing it in that order, that means if that spot ends up being needed later, then you have to do that again?
yes.
There's
you
also
go again.
quadratic probing, which is fun.
Yes, where
Okay.
you multiply the value. Instead of adding 1 to get the next spot, you would multiply it by 2.
So in this example, then none of that happens, right? It looks like they all just go in normal, or
Yeah.
was there a
So,
little thing I missed?
in this case, what happens is you get H, 0, put it in slot 0.
Yeah.
R gets 3, you put it in slot 3, 3 down
Yeah.
here. Then you do
N5.
M5, X2, Y4.
Oh, because it's
Sorry,
three.
Y goes into 4 because
Y
R is-
3 plus 1 is 4.
Yes,
Yep, I
because
gotcha.
Y gets 3 and goes into the next available slot.
Okay.
And then
I is 1, it just goes there.
and goes
Okay.
in. Yep.
This is
So-
kind of fun.
If
That's not
you
that bad, I
hash,
was expecting it worse.
if I were to hash B and P,
Mhm.
and then want to access them by value 1, which one am I gonna get?
So you're going to put it through the hash function to get 1, and then that means you're going to start searching at 1 for that value, and then you're actually going to compare and make sure it matches.
And if it doesn't match, you just keep moving until you find
So you can't actually like read a value from a hash table?
You can, sorry, yeah, so let's say you have B and P, say you put B and then P, so you would get B and then P, and you want to find P. You would start at 1, and then you'd say, is this B? Is this P? No, it's not. Go to the next slot. Is this P? Yes, it is.
Well, I mean, but I would already have to have known that I wanted P, right?
Yes.
That's what I'm
because you're
saying.
searching for it.
So, sort of like in a binary search tree, you can have your key different from the value. So I could store, say I want to store like any kind of data structure or any class, any object, and I want to give it, I would have a key of P, and so you would compare its key, and then that would give you then maybe a pointer to an object.
So you're hashing the keys, not the value?
Yes.
For Minecraft uses
Exactly.
this for their block information. It will store all of the blocks as just simple numbers in a tree array. But then when you want to, say you want to interact with the block, it says, okay, what block I'm standing on? Okay, block ID 4, go down, and block ID 4 is like grass. So play the grass sound. It starts with a simple ID and it goes to a hash map to fetch the actual behavior of the thing you're touching.
So say Carl is stored at key W. Okay, well, I know that it has key W, but I don't know that it's Carl, but I know it's key, so I can start here, then go here, then check if it's W. Okay, and then I can get like a reference to that object. from that. Make sense?
So like, I think I got it, just to clarify. This hash table is to map what like an AVL tree is to a map. It's just a way of storing things.
It's a way for you to index things, it's a way to index an array without necessarily using integers.
Yeah.
You can pass in strings as keys, as an STD map. So you can pass in strings and it gives you some other value that you store in there.
As long as there is a hash function defined for the key type that you pass in, then you can use that type as a key.
Yeah, because a student by default does not have a hash function, but a string usually does.
So then you could associate a, so you can associate a string with a value and then use that string as the key, and then it becomes kind of a lookup table. Oh, I can look up that key and I get the value.
And this is what hash array is?
Yeah.
I don't know, I haven't done that one yet.
Yep.
Probably.
That was one of my favorite ones from
Is
this
it
class.
easy? Tell me
Yes.
it's easy.
I did it in a couple hours.
Okay, for each character in the hash, calculate the number of probes required to find it, assuming linear probing again. So, I assume, at least because it doesn't mention. So, I guess I'll scroll back up a little bit so you can see the key.
The only thing, all these are 0 except for,
Except for Y, right?
So
yes, Y has 1, the rest have 0.
H is 0, R is 0, oh wait, sorry, R is 3.
What?
What? R has a key of 3.
Key,
Yes.
not the number of probes.
Yeah, we're looking
Oh,
at the
oh,
probes
sorry,
here.
yeah, sorry, I was
All of
writing
them
out the
have
keys,
probe
yes.
0 except for Y, which has a probe of 1.
It
Yes.
starts at 0, not 1?
Yeah,
Okay.
Yeah.
as most things in computer science.
So, would the initial probe count as a probe though?
It's a good point.
I think it
Let's say
would.
yes.
Yes,
So
so
all
all
of
of
them are
them.
1 except 2.
Yes, all of them would start at 1, and then if you need to go to the next slot, it would be another one.
Yep. So all of them are 1 except the Y, which has 2. That's easy.
It is 1.
And
Okay.
the reason for that is because all of them have different keys, or sorry, yeah, different keys,
And so like hypothetically.
except for Y.
Like if Y had for some reason gotten booted down to like 6, right, that would be, what, because it's supposed to be a 3, so you look at 3, and then it's 1, 2, 3, like you add an extra probe for every level you have to go down. I don't know how to
Wait,
make this make sense in a way that,
how is X 1? Because X should be 2, which would be here, so it should require 2, right?
Oh, I looked at the W key.
Yeah, okay, so I'm gonna write the key of each letter next to it, and then we'll figure out the number of probes. So H has a key of 0, R has a key of 3, M has a key of 5, X has a key of 2, Y has a key of 3, and I has a key of 1. So for H, we look at its key slot, which is 0, so that's 1 probe.
yeah.
For R, we look at 3, which is 0, 1, 2, 3. So we start here and we say 1, 2, 3, 4, 5.
Okay. So
So
it's
that-
in that order, not the order we did before.
Yes, so it
Yeah, that
requires
makes sense.
5, which is the same order we
Wait.
insert them in. Sorry, it's the same way you look at it when you're looking for a spot to insert
Why would
in.
it,
Okay, wait, hang on.
why would it include 5 probes?
Because,
You're going
so,
down.
so R has a key of 3, which means we start, okay, these are the actual indices.
Yeah, I was gonna say, we
Of
use
the
like so
slots.
many numbers.
And then these are the keys. So we start, so it has a key of 3, so we're looking up 3. So we start at index 3.
And when R, wait,
R is at index 1.
it is?
Yes, it
Yes.
is. Because
0, 1.
this array is index 0, 1, 2, 3, 4,
This
5.
is using
Oh, these aren't
this
the same
order.
ones
Yeah,
that we
yeah,
just
it's not
did.
the same
Oh my
order that we
goodness,
just did.
okay.
He used the same, it's a different problem, so it's using that order, not the one we just made.
I
like-
see,
like
okay,
before.
the one that we
Even
did
though-
before
Even though he used the
was-
exact same letters and it was a horrible.
Inserted in the exact same order. Well, they're
Yes.
not inserted, but they're written the same order.
Yes, exactly, which was horrible on his part, but you know, that's fine.
Thank you, Volper.
That's Volper in a nutshell for it,
Right.
yeah.
Okay, so
Yeah, yeah, yeah,
the
yeah.
the
Oh,
old
wait.
one was 1,
Yeah,
No,
1,
it has to
1,
be the
2,
same
1.
one, right?
No, cause I don't,
I feel like that's implied.
They're the
Wait,
same-
oh,
They are
is
the same
it?
characters
That's
and
a-
they are in the same hash.
That's a weirdly phrased problem then.
well, cause my thought process is, if you wanted us to
It's
use
a-
the same thing as the last problem, it would have been an extension of problem 5, it wouldn't have been a new problem.
Yeah, so this is the same letters but using a different hashing
Sure.
function,
Let's just,
I think.
well,
Maybe.
well, we have to assume it's the same hashing function, otherwise we don't know what hashing function is used to generate the keys for each of these.
Okay, so they just got placed in random places for this.
No,
Yeah.
that's not necessarily, where does it say that?
Well, but if they
So,
weren't in
okay,
random
alright,
places,
alright,
there would be where we
The
put them.
main idea here is this is an ambiguously written problem. We don't know if this means that this is the hash, that this is the resulting hash table that we're supposed to look up from, or if this is just a spot to put each of the answers for the previous, using the hash table that we wrote for the previous question. Let's.
I feel like I feel like that's implied, because, yeah, it says 5, 6, 7, but it's still part of the same, like, hashing question. I don't know.
Okay,
We could just
We-
ask him day of.
Be like, tomorrow we show up at 9 AM, okay, Volper, before we do the final, we have a very
Okay.
important question for you.
So-
He's chill during the final, when this comes up.
Okay.
You just ask him.
Yeah, that's true.
we can do this. We're gonna write out, what was the, did anybody write down what we
Yeah,
wrote?
Yeah.
so it's HIXRYM.
HIXRYM. Okay, now these are going to be the indices and these are gonna be the keys. So 0, 1, 2, 3, 4, 5, and then the keys are 0, 1, X is 2, R is 3, Y is 3, and M is 5. Okay, so it is actually what you were saying. So we look for H, then we would see, okay, we only need 1 because we start at its key.
Does the number of probes also include the time in which you, like, looked up the initial one?
Yes,
Okay.
because you're probing it.
Okay, fair enough.
And then I, same thing, X, same thing. Sorry, what am I? Wait a
Those are
second.
not the right
That's
letters,
not how
but,
that
you know.
works. I would also take 1, X would take 1, R would take 1 because we see its key is the same as its index. So R would also take 1. Now for Y, its key is 3, so we would start here at 3 and then we would have to go down 1 to get to Y. So that would be 2 probes. And then M is 1 again.
I
So-
see, he just mixed them up so it wouldn't give you the answer at 5.
Yes. He gave you the same order that you inserted them in 5.
I see.
Which doesn't end up being the same order they
Yes.
result in the hash table. Yeah.
Okay, just Q, C, W, calculate the number of rows regarding character behavior is not in the hash.
Okay. So, for characters QCW, I see, okay, so this is using the same hash table, again, we're assuming, and it's saying, these letters are not in the hash table, how long does it take to determine that they aren't?
2, 3, 4,
Well,
5.
Is it not just going through the whole, all 6 every time and then being like, oh no, it's not there? I feel like that's.
Oh, yeah,
probably
does it
the-
reset?
No, to find something not in the hash, you have to find the first empty spot.
Oh,
And there are.
oh, I see what
Yeah,
you're
there's
saying.
one empty
And so
spot.
you
And there
start
is
there
one
and it's
empty
B.
spot at index
6.
6, which means that, okay, so Q, the key for Q is 2, so we would start at 2,
Mhm.
and then we would go 1, 2, 3, 4, and then we see 6 is empty, so
So 5.
5, sorry, let me do that again. Q, we started 2, 1, 2, 3, 4, 5, it's empty, 5. C is index, or is key 2, so 1, 2, 3, 4, 5 again. And W is key 1, so 1, 2, 3, 4, 5, 6. That's 6 steps. Now, if there was an empty spot at, say, 3, and we started at 1, then it'd be 1, 2, 3, and then you'd be done.
Okay.
If there's an empty spot, you stop immediately.
What
And
do you
if
do
the-
the thing is full?
Yeah, if it's full, do you go in a circle until you hit your thing again that you
If
started
it's,
at?
if it's full, theoretically, you would go infinitely,
Great,
Yeah.
but
okay.
That's why you have a
practically,
load factor.
practically, you stop. But yes, that's why the load factor, which we talked about in the lecture, theoretically, its limit is at infinity, not at the size of the array. But practically, you would stop once you go through the entire array. Which means that searching for something that isn't in the hash is typically slower than searching for something that is in the hash, which is weird. Not always, but typically.
There's no way of like,
So this hash table can only hold 6 things at a time, or 7 rather?
Yes, and then you would have to dynamically grow it like a vector, and you would have to reinsert
We have to
everything.
we have to change something as well? Because it's a
Yes.
modulo 7?
Yeah.
So you have to modulo, you do the 14 or something?
Your hashing function has to map all the possible values that you could take into a space that fits it within your table.
That's why most hash functions often use modulo.
Yeah. Cool. How much did you guys see of binary heaps?
We did do
it's
the,
a line.
yeah, we did do binary min heaps and max heaps.
Cool.
Did not do binomial heaps.
I don't
Yeah,
know what a binomial
I
heap is,
think we
so-
said that binomial heaps are not gonna be on
Yeah,
there.
they're not.
I don't remember us talking about those at all, so it's fine. All right.
Because when we
Question.
went over heaps, I was half asleep in a grocery store, so I wasn't paying attention to the lecture.
Questions on this?
No, that makes sense.
Okay.
That was, I was
Cool.
expecting that to be way more complicated.
Yes, it's actually very nice. And also,
And the chip size?
because of how you construct them, they are actually relatively efficient for data storage and stuff. It's just the only operation that isn't always efficient on a hash is iterating through each element of it because there are a lot of empty slots that you would have to skip.
What is
So-
heapify?
means it's
Heapify.
It turns an array into a heap.
What is a
Whoa,
heap?
with heapification being
No,
on it.
no.
What?
Okay,
Like
but
This
has
is a
to-
function we wrote for the binary heap lab.
Yeah.
Oh,
I didn't
no, I
do
just,
that.
I didn't.
Okay,
so
well,
a heap-
that's why we're reviewing
Yeah,
it.
a heap is like a tree in which both childs satisfy some condition over the parent. So like,
So
I
it's
mean-
a sort of lazy sorting data structure where it's not fully sorted like a binary search tree. Only the root is actually guaranteed to satisfy the sorting condition that you specify, such as minimum or maximum or whatever condition you want.
Diddly deep, you are now a heap.
So, so in this case, for a min heap, it means that the root should always be the minimum value or the minimum key in the tree or in the data structure, because you can represent it as a tree or an array. And all the other ones generally follow that rule where their children are greater than them, but it doesn't mean that all things on lower levels have to be greater than them, just their direct children have to be greater than them. So, we want to build a binary min heap from the array 5392174, which means that we should follow the insertion algorithm for a binary heap, which involves bubbling up and trickling down. So we should start by inserting 5.
5?
Yeah, we want to insert them in this order.
Show every step.
It says to.
yeah, the
Oh,
So-
oh shoot, I forget. Which one is the better algorithm? Is it the bubble up or trickle down?
trickle down is technically better.
Is that the V2 algorithm that you told us
Yeah,
about?
that's the V2.
Trickle down, cool. Which means that you would,
But it doesn't necessarily say, I guess here it doesn't specify which you use.
One to binary.
oh, but it does want heapify calls, so it implies trickle down,
Okay.
because heapify is trickle down.
So how does,
And change key is bubble up.
Yeah, it's weird that they're named that.
Yeah.
how
That's-
does the steps go? Is that,
Yes. Is that what you're doing right now, Seth? Okay. So we're gonna start with this array.
uh-huh,
And we're gonna insert each of these into a heap. So we're gonna represent it as a tree first, and then we can represent it as an array. I'll show you how to figure out the representation between those. Cool. That's awesome. So, first we're gonna insert 5. Then we're gonna insert, can you give me a refresher on how trickle down works? Is it you insert at the top and then trickle it down?
No.
The way I did it was, I did it at the leftmost empty slot. So like, let's say this one's taken up, all right,
Mhm.
okay, boom, I'll go right here.
Mm-hmm.
And then if this is less than this one, I swap them. And I continue swapping up the tree until the heap condition is met.
Yep, and that's called bubbling up.
Yeah.
does the trickle
Trickling
down
down
work?
is,
Do you insert above and then you move it down?
well, you don't
until-
typically insert at the top of the tree, you insert at the bottom.
Right. Oh, shoot, what was the heapify function? Because it wants heapify calls. Hold on.
Yeah, I'd have to recall.
Give me 1 second. Oh. Perfect. So heapify.
Oh, I see.
Okay, here we go. If it's a leaf, I see. If it's not a leaf, find the smallest child. And then if the smallest child is smaller than the index, swap them, and then heapify the child. Hold on. If index is not a leaf, find the smallest child. Okay, I see. Okay, so we can actually start by representing this array as a tree. I'll show that first.
Okay.
So the way we define this is that to find the left child of a spot, you multiply its index by 2. And that's indexed off of 1, I think. Oh, sorry, you multiply its index by 2 and then add 1. And then for its right child, you multiply its index by 2 and then add 2. So the first one is going to be the root. So we say that's 5. Then its left child is going to be 0 times.
Oh, I see, okay, yeah, that makes sense.
Its left child is going to be 0 times 2 plus 1 is 1. So that's 3. And then its next one is going to be directly after that, and that's 9. Then for 3, it would be 2 plus 1 is 3. And, index 3, which is value 2, and 1 is directly after that. And then for 9, that is 2 times 2 plus 1 is 5, so you get 7 and 4.
Okay.
And then
What do you do to the index to find the right child?
you multiply by 2 and then add 2. So, yeah.
I see, okay, yeah.
And then to find the parent, you can actually do index minus 1 divided by 2. And if you do integer division, that will work for both the left and right children.
And then assume if it's an array overflow, then it's no child.
Yep, exactly. If it's out of bounds of the array, then that means that it is not, then it doesn't have a child at that position. Which means that in a heap, you will never have a right child but not a left child. All of the leaves are pushed to the left as far as they can go. And then if you follow only operations that work on binary heaps, then that condition will remain the whole time. So you won't have a right child but not a left child. And because of that, because there's no gaps, you can represent it as an array.
You said to find the parent, it was index divided by 2.
Index minus 1 divided by 2
Index minus 1.
with integer division, so truncating on halves.
Most of those parents are larger than their child.
Yes.
So they haven't started the heap.
So this is not an actual min heap yet. This is just the direct representation of this array as a tree.
Oh,
Now,
I see, I wasn't paying attention.
yeah, now we need to heapify it, which means to
Turn it into a.
so there is a thing where you, okay, so the V2 algorithm we talked about in class, which is probably what he wants because he wants the number of heapify calls, and that's the one that involves heapifying instead of, so that's trickling down instead of bubbling up.
Yeah, it's here in this notes called binary heaps.txt.
Yes. So what we do is we start at the index of size over size half of size divided by 2, and then we go down to the minimum index, and for each of those indices we trickle it down, which means to find its smallest child, swap it with its smallest child, and then heapify it again. So trickle that value down until it is greater than its parent. So what that looks like is 5, find its smallest child. Yes, because we want the minimum to go up. So find its smallest child, which is 3, swap it with 3. And then do it again. So find its smallest child, which is 1, and swap it with 1. Wait, I started at the wrong place. Let me
I
undo
think
that.
you started right, because you gotta restart at 3 again.
Yeah, no, I started at the wrong place.
So 4, 7.
Okay, so we find our size is 7. We want to start at 7 over 2, which is 3.
3.
Yeah, so we
So
start at
0,
9.
1, 2, 3. We start at 2. What?
Huh, that's odd.
Well, no, his is 1 based.
Oh, okay, so 1, 2, 3. Yeah, you're right, it is. So we start here and we say, okay, is it greater than its smallest child, which is 4? Yes, swap them.
Sorry, why did you start at 9? I know you just, like,
So
I just didn't fully.
the reason we start at 9 is because if we heapify the top half of the tree, then, or if we heapify everything besides the leaves,
Mhm.
we never have to heapify the leaves because they don't have children to heapify,
Right.
to swap with.
Okay.
So we know that they are already all satisfy that condition, so we don't need to check them.
Mhm.
And size over 2 means everything besides the last layer,
Okay, that makes sense, yeah.
because it's a binary tree.
So you just do basically the last thing going like this until all that's left down there is
Yes.
children?
So you start at this, yes, you
The
start.
last thing that has a child, I should say.
Yes, you start at the second to last layer because that's the only layer that has children. So we swap with 9. Now 9 is a leaf, so we know it's heapified. Now we start at 3 because it's the next index down. So index 2, value 3. Is it greater than its least child? Yes, which is 1. So we swap it. Then we go down to, and then we say, okay, is this heapified? Yes. Now we go to 5 and we say, is it greater than its least child, which is 1? Yes, swap it. And now we need to heapify this index because it's a recursive call. And we say, is this greater than its least child, which is 2? Yes, so swap it. Sorry, I wrote 2 again.
And then we're done?
And then
Yeah, you're done.
we have heapified this one, and that means we've reached the end of the loop. Now we can verify by saying, does any parent have children that are less than it? No, all the children are greater than their parents, which means that the topmost root node is guaranteed to have the least value.
Which is also the set code.
What?
The same tree, the same results tree.
Yes.
The 9 and the 7 are swapped,
Yes.
but other than that.
Oh, well, not quite. The 7 and 9 are both on that one.
Because you wrote it in
Yeah,
a different
yeah.
order. But that still satisfies it, but this one is the specific one that you would get from this
I mean,
starting order.
The way he wanted you to do it, the way he wanted it.
And to do the heap, so the heapify calls is every time you make that check of, hey, is this greater than its least children? And you would count those. I forgot to count them.
It's 4 steps.
4 heapify calls,
Yes.
or 4 steps total?
4 heapify calls.
Same.
Four heapify
It
calls?
says the number of steps should be the number of heapify calls. So,
Oh,
so it's the same thing.
I see.
Yeah.
Cool, awesome. And then to represent this as an array, we would start here and say 1, and then 2 immediately follows, and then 4, and then 5, 3, 7, 9. And you can see while not everything to the left is always less, so it's not a sorted array, like 3 is not left, or 3 is not greater than 5, but it's on the right, it's still okay because of the binary representation we're using. And because it doesn't, like, for example, 5 is greater than, 3 is less than 4, but it's still below it in the tree, but that's okay because it's greater than 2, which is its parent. So we don't need to sort everything, only this needs to actually be fully sorted, and the rest are lazily sorted.
And now we have to go on to part B.
Now, delete the top element.
And how many-
Okay.
How many calls is this?
4.
4.
Probably not gonna get this on a test.
Okay, so deletion for this is kind of cool. All you do is delete. I'm kidding, but
Oh, oh, I was so excited for a second.
It's pretty close to that.
but now all you have to do is say, okay, well, what is the easiest way to restore the full tree structure? Well, what can we remove from another part of the tree that won't destroy the tree structure? We can move 9, so we put 9 up here. Oh no, this is now not a min heap because 9 is not the minimum value.
No.
So what do? Heapify it. So we say, is it less than, is it greater than its least child? Yes, which is 2. Swap it with 2. Heapify, is it greater than its least child? Yes, which is 3. Swap it with 3. Is it a leaf? Yes. Heapify, you're done. And we can verify 2 is the least and everything's child is greater than it.
So when you deleted the top one, the 9 went right there,
Yes.
right?
So
Okay.
you delete the root, you take the very, very last element, move it to the front, and then heapify the root.
Why did we do the last one?
Because that's
Because-
the only node that won't destroy the entire tree.
Yes, it is the only node that is guaranteed to not have anything to the right of it, nor any children. Which means then you don't have to move other stuff when you move that. And the complexity for this deletion is
Log n, I think.
log n. Anybody know why?
Binary.
Yes, because it's a
Sure,
binary
log.
tree. So every time you go down a layer, that's a log n traversal down to the bottom. So worst case scenario like this, where you had to go through each layer, that would be log n steps relative to n the number of elements.
Yep.
And this would be in linear.
What?
If you're in linear representation, it's become 2, 3, 4.
In linear representation, it's still log n.
No, you mean like the array.
Yeah,
Right
it's
now,
still
No,
log
he's
n.
asking what the array looks like.
Oh, sorry, you want to see what the array looks like?
Yeah.
Oh, sorry, yes. So now it would be 2, 3, 4, 5, 9, 7.
The array is just it in level order.
Yep,
Okay.
exactly. And because there's no gaps, we can use that simple mathematical formula to find the child, which makes it very fast. Because also you don't have to do pointer dereferencing or anything memory access that isn't just an array access.
I still hate pointers.
I will miss them in
C sharp.
I was gonna say Unreal, because I just want to use Unreal.
Yeah, I'm not.
Okay. Any more questions about this, about deletion or binary heaps? Any? Okay, moving on. How many questions are in this?
13.
Okay.
We have
We have 15 check at least 1 minute, and there are 13 questions. So
Well, we
5
can,
more.
we can stay
One per
after.
minute, let's go.
Yeah.
Yeah, Seth is the only one that has to leave, right?
Right, which is,
Yeah, I gotta leave it too.
yeah.
No
Okay,
worries.
that's okay, we can keep going.
Oh, there's so many questions.
Okay.
We can skip 9.
Why?
Binomial
we have
heaps.
Oh, binomial min heap, yeah, we're not doing that.
Why no?
Okay,
10, no.
for the given directed graph, fill in the table with in degree and out degree.
Yep.
Maybe graph theory.
What are in degree and out degree?
I don't know.
It's the number of edges that are directed in towards the vertex
Versus
and
out.
the number of edges that are directed out.
Okay.
Wow,
Instance,
no,
you
please.
have 2, 1.
Yes,
Why
example, A has 2 arrows going out, so as an out degree of 2.
Oh, that's not that bad.
And then it has 2
Oh.
arrows
I
going in.
don't, I don't remember that terminology being.
I don't
Discrete
either,
math, let's go.
but discrete math, why are people not required to take discrete math while they're taking this class?
I don't know, but discrete is fantastic.
Discrete is great, it makes this a lot
Huh?
easier.
I gotta leave.
You got
But
discrete
it's a
math.
good class.
So,
That's a good,
to summarize,
That's
Nice.
really
Yeah.
funny, that's a cool
Didn't
course.
to
remember shit about
summarize,
class.
in degree is how many arrows or node or edges point in, because it's a directed graph. Out degree is how many point out, because it's also still a directed graph. Cool. Rate an adjacency list.
What's a non-directed graph?
Non-directed
No
graph
arrows.
means there's no
It's
arrows,
just
and it means that
lines.
basically all the connections go both ways.
Yeah.
Double lengthwise?
Although you can
Kinda.
have a directed graph where all of the connections do happen to connect both ways, but it would still be directed because the different
Yeah,
edges could have
arrows.
different weights and things like that. But basically, if there's no direction necessary or specified on the graph, it is an undirected graph.
For instance, it takes less time to fall off a cliff than it does to climb up it.
Yeah, even though you're getting from the same point to the same point, or like getting from one point, getting between the same
So
two
it would
points,
be
there's a different
The
weight on the
weight,
edge.
the weight of the direction.
Yeah.
would be different.
For example, a tree is a directed graph because you can go down to a child, but you can't go back up to a parent. And if you had a parent pointer, that would still be a directed graph because you go down and then you could go back up. A tree is a type of graph.
Yeah.
Okay. Write an adjacency list representation of this graph. This means to write a list for every node. What nodes can it go to?
I'll just draw the picture over on the side.
What?
Can I borrow a marker?
Yeah.
Oh, that was the
Oh,
whole thing.
okay.
No.
Here, I will write an adjacency list representation of this graph.
So I'll draw the
Oh,
graph
you're redrawing the
here.
graph. Thanks, appreciate it. You wanna use the red?
Oh, I was so
That would
good.
be nice.
Oh, no, it looks horrible. What is that?
Just zoom out one now.
What?
Zoom out.
Oh, I forgot that's a thing.
Oh, yeah, you could do that. I just had it zoomed in so we could.
Oh, I wanted to do something.
It'll just be faster. Just like that.
Oh.
I mean, you
Matrix.
can try if you want. No one's gonna stop you if you wanna live out your
No,
dreams.
it's.
Okay,
fine.
so-
I haven't done matrices in a year and a half.
So, adjacency list representation means that for A, B, C, D, and E, we're going to write a list of all the nodes you could get to from that node.
Oh.
That, basically, you just look at it and see, okay, we can get from A to B or A to C, so it'd be B, C. From B, you can get to C. From C, you can get to D or E.
Don't you also want to write the weights down there associated with these?
Yeah, probably. Write a number associated with each item, but in this case, I'm not gonna bother. For D, and that would just be taking the number on the arrow that connects to it and noting that with the letter. D, you can get to A, and E, you can get to A.
I know, yeah.
This is an adjacency list representation of that graph. Somebody remind me, are adjacency matrices true-false tables?
That depends on.
Or, you would write the weights, you would write the weights.
Yeah.
Okay, so an adjacency matrix, you have a table that goes, let's say this is, the from is the, like this, the side, the side, and this is 2. So you say from A, B, C, D, E, or F to,
There's no F.
oh, there's no, yes, there isn't, you're right. To A, B, C,
D, or E. And it's a table, it's a,
Bye, thank you.
Okay, well, I think they're probably coming back.
no, they didn't take their backpack or anything.
Oh, okay.
Yeah.
Cool.
Fooled us.
Cool. So, what you say is, okay, so from A to A, you cannot get to it because there's no like looping connection. So we specify that as an error value, -1, assuming we can't have negative weights. Otherwise, you would choose like not a number or something like that.
Infinity.
And you wouldn't need negative weight.
Infinity might work depending on how you're, how
You
you're
can also
using
say
it.
A to A is also 0.
You cannot because
Only
then
if,
that
only
would
if your
imply-
graph is defined to allow connections to itself.
Yeah.
Yeah,
So-
because in that case, you could say you could go to A to A through an edge, which is not always the case.
Okay, next one is from A to B. I'm gonna write these in more descriptive places. Okay, from A to B, you can get to by a distance of 4. From A to C.
It's a distance of 1.
Oh, I was reading B to C, that's my bad. Yep, distance of 1. From A to C is a distance of 2. From A to D, can't do it. From A to E, also can't do it. From B to A, well, we can actually just look at this. The only one it can go to is C. And its distance to C is 4. For C, it can only go to D and E. And its distance to D is 3. And its distance to E is 2.
Are both of those two the ones we can't see?
This one is a 2.
Loopy ones?
That one is a 1. E to A is a 1.
Okay.
Okay, D can only go to A, and that distance is 3. And then E can only go to A, and that distance is 1. This is an adjacency matrix representation of this graph. Because we have a slot for every node, from every node to every other node, it means we can directly represent every possible connection and whether or not it actually exists, and its weight.
Shortest cycle is including weights.
Yeah. Any questions about that?
No, that actually kind of makes sense.
So that only includes things that you can directly get to?
Yes, adjacency, so
Okay.
only adjacent nodes.
So there are 2 cycles, it looks like.
Okay, so cycles means you can get from a node back to itself through some path.
BCD cycle.
Trees do not have cycles by definition. This is not a tree.
In discrete, they're also called circuits.
Cool. Okay, so shortest cycle, longest cycle, is it strongly connected? So let's see, possible cycles here include ADC, ADC, ADC. There's also ACE, 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 ACE is also a cycle. I don't see any other ones. Oh, there's
A, B, C, D.
yeah, there's ABCE, ABCE, and ABCD, ABCD. So we would need to find the length of all of those cycles and find the
I'm pretty sure
minimum.
the shortest one is ACEA.
Yeah. The
So
length is
let's
5.
see, ACEA has a length of 5. The other ones all include ABC, which is already 5 plus more, and ACD is longer than 5. So I'm happy to say that that would be the shortest one.
Wait, hold on, what's like an ACDA?
ACEA has a length of 5.
ACDA has a length of 8.
Eight.
Of 8. It's the sum of all of the
AC.
weights.
ACEA, 5.
ACEA is 5, yeah.
And
And AB, C, D, A.
11, I think, A, B, C, D, A, I think is the longest one.
Yep, I agree.
I tend to agree with that. A, B, C, D.
So we always rank the,
Huh?
so is it ACE or is it ACEA?
For which one?
A, C.
D, A, B, C, D, A.
A, C, E is the shortest one. A, B, C, D is the longest
So
one.
many letters.
Right, but do you write it as ACE or ACEA?
Just
The
the
second-
three.
Okay.
Oh, okay.
Because you assume to go back to the
I
first
guess
one.
that makes sense.
I mean, you could write either
I'm not
one.
Yeah, I don't think it's
Yeah.
usually
Yeah.
but.
It's
If you leave it at
technically,
E,
ACCEEA.
Yeah, you could write it as a
Just like
list
the
of
edges.
connections even would probably work better, yeah, a list of connections.
Yeah, I mean, technically, if you stopped at E, if you say ACE, it kind of implies that you stop at E, but I mean,
Yeah.
If it's asking for a cycle, it's assumed to be a cycle. If you want, you can write a series of connections.
I don't think he'll matter.
If the edges are labeled, you could write the edges as a list. Is this graph strongly connected?
Yes,
Why?
because starting at any node, you can get to any other node on the graph.
Are you sure?
Yes.
Yes.
Really?
Yep.
Yeah, not directly.
How would you
but-
get from C to B?
Go to E, go to A, go to B.
Good. Strongly connected.
And
Yeah.
alternatively go to D, go to A, go to B.
Go to, yeah, exactly. So yeah, strongly connected means you can get from any node to any other node. Is a tree strongly connected?
No.
Assuming no parent pointers.
No.
Correct.
One way.
Because you can only go down. You cannot go back up unless you
Way
have
to
parent
the
pointers,
middle.
and then it would be a digraph.
Yay.
Cool.
That was a long question.
Is that the end?
Oh, no, I hope so. I better not
No,
be more, because
Welcome back.
11.
Yay, Seth's back, yay.
Okay. Provide iterative implementation of breadth first graph traversal search. Provide iterative implementation of breadth first graph traversal algorithm. Explain how to modify the algorithm to switch from BFS to DFS. Depth first.
No.
Can we just
how-
not? Yeah.
Doesn't that have to be a tree, not a graph?
Yeah,
A tree is a graph.
Yes, but can you do depth first and breadth first for any graph? Or would you first find like the minimum spanning tree or something, run Kruskal on it?
Yay.
no
Because you
more.
could do that.
I feel like he wants us to assume that it's like a tree-like structure.
I don't know how to do any of those first searches on non-tree graphs,
Something like this.
but that's a tree.
No, it's not.
Yeah, it is.
Yeah, it is.
There's no cycles. Okay, now how do you define depth first?
Oh.
Yeah, I did.
Versus breadth
Let's
first.
assume that it's a tree-like structure. It's like-
Okay, well, let's make sure everybody knows how to do depth first and breadth first
Yeah,
on a
that's a
tree
great
first.
point. I think that's a good starting.
Cool. So we'll have a tree. We'll just say binary tree for now. Number of children really isn't too important. So this kind of is the same as the all the pre, in, post order traversals versus the level order traversal. But we need an iterative implementation of it, so implying C++ or pseudocode, which means that we need to say what the state is and what the operations are. So, oh boy, I need coffee. Okay, so I'm just gonna do the one that was kind of given in class and that we probably mostly used on the assignment for this, which is that we have a stack of nodes that are discovered, and when each of those is pulled off the stack, we add its children to the stack and search it. Well, we search it and add its children to the stack. So let's see. We'll have a stack visited node, discovered nodes, or like open nodes, or and it's going to be a stack of node pointers or a stack of nodes, and every time we visit one, let's see, we're going to start at the root.
Yeah,
Look at my
this
notes.
Just make an iterator and do plus plus.
Yeah.
For this, it's like a queue-like structure for breadth first search, because you insert the children into the back of the queue, and then you pop off the front of it. Then you pop off the front of the queue and process it.
For the answer, just write it plus plus. And
Okay.
have a little asterisk that says, assume iterator was already made.
Yeah. Assume iterator
Yeah,
implementation.
yeah, yeah.
Okay,
Assume iterator.
so here we go. I got it. Okay, so yes. Okay, so make a stack that is empty and stores nodes, and then I'm just gonna call it D because I don't want to write discovered every time. Yeah. Okay. Okay, so by default, we are always going to discover the root. Cool.
I'm good.
By default, we are going to discover the root. Then our loop is going to go until we have no nodes left, so we can say while the size of the stack is not 0, or is greater than 0. And then for every time we run this loop, we are going to, oh, sorry, we wanted to start with breadth first search, right?
Yes.
Yeah.
That starts with a Q, right?
Yes, it
Yeah.
does.
Okay, so so for breadth first search, a little spoiler, this is how you change between depth and breadth first search. We're actually going to start with a Q, which if you remember dec or the Q data structure means we can push to the front and pop from the back, or push to the back and pop from the front, I think is generally more what it is. Anyway, we have a push and pop that are on opposite ends, whereas a stack, they're on the same end. So we make a queue of discovered nodes, we push the root on, and then while there are nodes in the queue, which there by default will be at least one because of the root, unless it's empty, in which case we're already done, we will okay, there we go. Okay, so we will pop the, let's see, we'll make it, the node that we're looking at is the front of the queue. And then we are going to then do the search, so we're going to check to see if it's the actual one we want, which in this case, I'm just going to say we're going to return the node if it equals it.
Oh, front's not found.
Huh?
Okay.
Oh, sorry, yes, this says d.front for a queue.
Can't read. Illiterate.
And val is the search value. And we're just saying that we're going to return the node if we found the correct one. And then, assuming we didn't find it, we'll continue because return will exit the function. This is a function, an implementation for the search algorithm. We'll return the node. Otherwise, we will push its children onto the queue. Yes. And then repeat the loop. So I'll do a graphical explanation of what this algorithm is doing right after this.
Waiting for real this time. This is
Oh,
Bye, Sad.
Bye, Sad.
It was nice teaching you all. Good luck with the rest of your academic career or whatever. I'll never see you again. I'm kidding. I'll probably see you again.
Bye, Seth.
Bye, Sad.
Good luck with
Best of luck on your finals.
What?
Best of luck on your finals.
Yeah, it's great teaching you guys.
We appreciate you.
We appreciate you, dude.
Bye.
Bye.
Which is,
Yes. I'm gonna redefine this to not be left and right, but just push all of its children.
and and then you have to pop off the root.
And, I guess there's supposed to be a d dot pop here to remove the item that we got. Assuming C++ standard queue implementation. If your front also pops or your pop also returns the front, then you only need one, but assuming standard library implementation, you need both of these. Anybody remember why the standard library does it like that?
Why does what?
Why it separates pop and front or pop and top instead of being one function that returns and removes?
Well, what if you don't want both?
Right.
Yeah, that's my thought, like,
Yeah.
yeah, you just might not want both of them.
Exactly, but why?
To avoid expensive copy constructors?
Yes, to avoid expensive copy constructors when you just want to remove. Because even if it returns it, but the compiler doesn't optimize out that you don't want the return value, it'll still run the copy constructor to give you the value. Anyway, this is now the entire function, and I'll explain graphically what it does. So you start at the root, this is now discovered, and you say, okay, now go in here, get that off of the queue, and then check if it has the right value. We're going to assume it doesn't. And now push its children onto the discovered queue. So now this is the first item in the discovered queue. So next item we're going to check is this one. It's not the right value, so we're going to push its children onto the discovered queue. Now this is the next item in the discovered queue because it's a queue and not a stack. So then we discover this one's children, and basically you can see that we're adding them
Yeah, you're
in
doing it
rows
in
across.
layers.
And then we go to this node.
Bread first is this one?
And then we go to this node, no children, this node, children, children. So that means that what we've done is we've gone from here to here to here to here, 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 here. And then once we get to the end, the queue will be empty and we're done. And I guess, I guess you would return.
Yeah. I mean, it doesn't necessarily have to be a search, it just says traversal. You could do anything to those nodes.
Yes, so this is your so-called payload, which means this is, when you visit, you can do anything you want here. In this case, we're saying if it's the right one, return it. Otherwise, you can do anything else. You could say add one, that would add one to every item in the list, or
So,
in the tree.
why are we using a queue instead of a stack for
So-
breadth first?
Breadth first, what we want to do is we always want to visit the oldest node so that we start at the top and work our way down. So when we add a node to the queue, say we start here and we add this one and this one to the queue, then that means that the left node here is now the first one in the queue because it's first in, first out. So the first one we add will be the first one we visit next. And then once we visit that one, we add this child, but this node is still in front of it in the queue. So we then visit this one, and we add its children, but this one is still in front of those
Wait,
children.
it's for first in, first out? or-
Yes.
And that's just
exactly.
how queue works.
Yep,
Okay.
queue is defined as FIFO behavior, push in the front, pop off the back, push in the back, pop off the front, whichever one.
Stack, it's not.
Yes, stack is the opposite. Stack
FIFO.
is LIFO.
Yeah, that's the one, LIFO.
So, the next question is, or the next part is explain how to modify it to switch to DFS.
Luckily, you don't technically have to like actually write it out. Okay, never mind.
Yes, all you have to do is explain how to. In this case, you use a stack instead of a queue, and what that does is, instead of always visiting the oldest node that you visited, that you discovered, you instead visit the newest one.
So
So,
then it'll do like left first,
Yeah.
or,
it depends,
I
whichever
guess-
order you add them.
oh yeah.
So if you add the left one first, if you add the right one first and then the left one, you'll visit left first. So,
Right, okay.
say we start on, this is why in the lab assignment or whatever, you probably had to reverse iterate through the children list to add them to the stack. So if we start at the parent and we add right and then we add left, left is now going to be the first one on the top of the stack. So then we add left's child, and now that's going to be the top of the stack. So we add left's children, right, left, and now left is going to be on the top of the stack. We finish here, we exit from this one. Now right is on the top of the stack, and then we're done here, and we're done here. So then we go to right, we add its children, right, left. Left is now top of the stack, we're done here. We go to right, add its children, right, left. We're done here, done here, done here, done here, and done here, because we're done with all the children. So it would look like here, 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 sorry, that's wrong. Up to here and here, then to here, here, here.
Mhm.
So you can see we're always going to the deepest discovered part first. Another way to think of this is you can think of the sort of the group of discovered or previously passed nodes in depth first that looks like originally like this, and then like this, and then like this, and then like this. So you can see we're prioritizing breadth and then depth. And for depth first, it actually looks like this, and then this, and then this, and then this, and then this, including this one, and then we start going over here, and then 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 here. So we prioritize depth and then breadth. Any questions? Cool, perfect. And this is literally just, I copied this from my implementation of the lab. So, yeah. Oh. Semicolon.
You wouldn't get this
Pesky semicolon.
Yeah. You wouldn't download a semicolon.
Yes, I would.
Yeah.
People say like you wouldn't download a car. Like if I had the ability to, I fucking would.
In Rust, if your return statement is at the end of your function.
It's called modding Mario Kart Wii.
What?
Christ,
That was
loud.
That's
incredibly
happened
loud.
twice
Holy
now,
shit.
yeah.
Jump scare for the Wii remote.
In my defense, when I was setting it up, no one talked, and so I didn't have a way to fix it.
Okay, we're like in a, it's a house.
Surprise.
Okay.
Oh, hi, Jared.
And
Is
there's
that
like
you?
a, like
Yes,
a
it is
river.
Jared.
Like a
Yeah.
flashing village. And
Okay.
Jared kind of
Bitch
calls
ass,
it,
come
and
out of
can't
the
find it.
apartment and come
And
over
then
here.
Flashing village says, excuse David about
I need to
Mario
take a
Kart.
picture.
I was doing CS200. Give me a break.
Okay.
Well, now.
All right. Cool. If what was I saying now? What was I saying?
Well, you were specifically talking about.
Oh, yeah. Sorry. If your return statement is at the end of your function in Rust, you don't need a semicolon or the return keyword.
Isn't Rust trying to make it so that using their like logo is illegal or something?
They're putting very strict requirements on how to use their logo in your media, and yes, it is kind of dumb. But that's the Rust Foundation, not the Rust language. So.
True,
All right.
Rust Foundation does not sound super stable.
You're right. It doesn't.
Maybe they should take some keys in our language.
Okay. We only have one question after this, so we're almost done.
Yeah, go team.
Woohoo!
We're practically done with the exam.
We're doing it.
Yeah.
Doing it
Okay.
well.
Ooh. For the following algorithm, alg1, which takes an integer array called data from an unsorted array, and a collection called call that we want to initialize from the data. So this is when we were talking about data structures and their efficiency of initialization from an unsorted array. We want, let's see, the algorithm gets the maximum element of call of the collection, and then for I from 0 to 100, it will delete the maximum element, then insert half the value of the maximum into the collection, and then get the maximum element again.
What are we doing in this table? Are we filling in the time complexity?
Yeah.
Oh, no.
Okay.
Oh, I see. Okay, so it just wants us to see what are the complexities for each of the different operations for each of these different types of data structures, and then figure out what the total would be for all the ones that are used. in
Isn't
this
there
algorithm.
literally like a table on the notes somewhere that just has all of these?
Probably.
Probably.
Sounds like-
Yeah, this is just like a memorization problem pretty
So, well, it could be, or you could, if you know how each of the data structures works.
much. Yeah, either memorize the algorithms.
So is O of N, is the other array of O of 1 or O of N
What?
for initialize?
Oh, sorry. I mean for unsorted array, how much is the initialize? It'd be
Yeah.
O of 1.
Yeah. 'cause
Or
it's literally
O,
just
or O of 0, because you don't actually have to do anything.
Yeah.
But it's O of 1. So, let's do these in order. Binary heap, initialize.
That's N.
It's law. Oh yeah, it's the like.
Because of the V2
Linear-
version, he proofs with some bullshit.
Yeah, it's like, oh, since you're doing half the array, but then you're also doing that times 2 for the number, for the average, like the maximum number of times you would actually have to heapify or something, it's like N.
Okay.
Maximum is constant time.
Cause you just go all the way to the right.
Because it would be just be the root.
Yeah. It's-
Finding the maximum of a max heap is constant time. Because
But it doesn't specify whether it's a max heap or a min heap though.
Sure, but we're gonna assume it's gonna be the one that you would actually use in this scenario, which would be max heap.
Okay. But if you were using a min heap, wouldn't it also just be
It'd be
the last
log.
element of the array?
Not necessarily,
Nope.
because a lot
A
of
min
ones-
heap would actually not be able to find the maximum. There's
Oh.
no defined algorithm to find the maximum of a min heap besides traversing all of them and keeping track of the max, so it would be linear, I guess.
Gotcha, okay.
I don't actually know if that's, yeah, I think it's linear.
Well.
No, would it be n log n? Something like that. It would not be a well-defined algorithm, so we're gonna say max
All
heap.
it would technically, I think you'd only have to search the last, level, quote unquote, because, all the children have to be greater than all the parents, so at the bottom, all those nodes are greater than all the nodes that came before it.
That's not true.
Yeah, well, every child has to.
Oh, I see. Oh, if you're finding the absolute maximum of the set, yes. Yeah, sorry, yes. Delete, you can only delete the root of a heap, but then you have to do that bring up and trickle down, so it's log n. Because that trickle down is log n because it's the number of layers. Insert is insert at the bottom and bubble up, which is also log n. Yes, so also log n. Total time to execute out1. This is going to be, we have a constant number of deletions and insertions, and each of those, they're not multiplied, they're added and initialize, and I think it'd be n, right?
You're just adding all of, is this the same thing like before
Yeah,
where
I
you're
think
adding
you would
these
just
together
be-
and it's whichever one's the
You
longest,
would
the
just
biggest?
be adding them all, yeah.
Okay. Here, I wonder if I can pull up the,
Because you're not deleting inside of the insertion algorithm or anything like that, I think.
yeah. Let's see.
Probably just log
Oh,
n
here we
then.
go.
Or it'd be log n.
Or no, because n is.
Because n is greater than log n, yeah.
So is total assuming that it's like a big O notation where you throw away the previous one, or you have to add them all together?
Oh, I guess we could do n plus 2 log n or something.
Would it be 100 since there's 100 elements?
Sure, we'll do n plus
I guess if it doesn't say thing.
plus 1, which doesn't actually mean anything, so, because that's just for the maximum.
Okay.
You know what? I'll write it like this. If you want to condense that down to big O notation, that is n.
Yeah.
Because if it was this times this, then it'd be n log n, but it's not. What's log n times log n?
Log n squared.
Is it log n squared? Is it not just, is it not n? I don't know.
No.
I don't think that's how that works.
That's not how it works.
Cool. Well, that would be root n
That's
times
square
root n
roots.
would be n.
Yeah, that's
But
not.
close.
Log n to the power of e would be n.
EA sports, what a shame.
Okay, oh.
Okay, unsorted array. to initialize an unsorted array from an unsorted array is constant time. To find the maximum is linear time. To delete is linear time. And to insert is also linear time.
Is it? No, it's not linear delete.
Why not?
You need to shift.
Yeah.
Well, yeah, it's
Shift is linear.
Oh, right.
Because if you're assuming worst case, it means you'd be, oh, yeah, because it's finding maximum, so we don't actually know which one that is. Now for sorted, that could actually be different because we're finding the maximum of a sorted array, which means that would be constant time because you don't have to shift anything.
Not necessarily, if you remove, oh wait. For which one?
For sorted, once we get to sorted. This one is gonna be
100 times 3.
3, and, oh yeah, sorry, it would be
I mean, I don't know if we're actually doing 100 thing or
3
not. but-
times,
310, yeah, it's 100 times 3n.
yes, sorry, yep, you're right. It'd be 100 times 3n. Big O is n. Now that I think about it, deletion of the maximum for binary heap, yes, will be log n because you're bringing a non-maximum up to replace it. Insertion, you're not inserting maximum, so it would still be log n. Sorted array, the definite minimum time to sort an array is n log n. That's just a thing. There's a whole proof for it that he showed us in class. I don't remember what it is, but sorting an array is n log n complexity.
Maximum is constant.
Maximum of a sorted array would be constant. Deletion of the maximum from a sorted array is also constant. Insertion of non-maximum into an array is linear for sorted array. And total time now would be
And square
Oh.
log n.
would be n log n plus 100 2 plus n, if we're doing those.
Or O of n
Or O of n log n, because n log n is greater than n in growth time. O of n log n is greater than O of n.
And just to make, oh wait, never mind.
And the reason deletion of the maximum of deletion is constant here only because we're specifically deleting the maximum, and the maximum of a sorted array.
We know where
Oh,
that is.
sorry. Insertion into a sorted array is
Yeah, it's not. You have to resort it afterwards.
insertion. Sorry, is linear though for one element. Sorry, a sorted insertion would be linear because you would scan across the array until you find one that is less than the one you're inserting, and then you can insert there, and then you have to shift, which is linear. So it'd be 2n, but that's still n. Same complexity. Okay, actually no, it'd still be n because you're only shifting the amount that you didn't pass on the way to get there, so. Okay, BST, binary search tree. Anybody know the complexity to initialize a binary search tree from an unsorted array?
N log n.
Yes, because you're sorting it. So you cannot get shorter than n log n. Also, log n shows up in trees, so we're just gonna say that. So n log n, because it's a sorted, because it is a sorted tree, you cannot get shorter than that. Maximum of a BST. What's the maximum algorithm on a BST?
Oh,
Right,
it's,
most.
So you
Just
just
go all the way to the right.
Yep,
Log n.
and what's the complexity of that?
The
Log n.
Log n.
Oh, log n, okay.
Because,
Yeah, keep it down log n levels.
because you will have to go a maximum, oh, he did show up.
Yo!
Hey!
Yay!
Not sure how many there are. Because you will only have to go down a maximum of the number of layers there are, and the number of layers is logarithmic of n. Welcome. Deletion of a binary search tree.
By the way.
Anybody know deletion of the maximum of the binary search tree?
Also
Log
log n.
n.
Yeah,
Yeah,
and it
there's
wouldn't
no
have
maximum.
children.
And it
as
wouldn't
well,
have children,
it's just
so it'd be,
easy.
yep.
Wow, that's crazy.
Anybody know the insertion of non-maximum of binary search tree?
Log in?
Yeah, I was gonna say.
Pretty
is it
sure
just
it's
log
also
in
log
again?
in.
So, do we know if there's like a place on his website that just has these written down as a memorization thing, or do I just use this?
Just trees are logs and arrays are ends.
Because when you cut down a tree, you get a
So the way to
log.
do
Oh,
it,
that's exactly.
the
it.
proper way to do it is to know how all of these data structures work enough that you can recalculate it on the fly in your head.
Yeah, see, that's.
Otherwise, there's probably notes on his website that you can use to look it up.
Yeah, I was just curious, I don't know if that was actually there.
So this would be n log n plus 100 3 log n.
That seems long to me, but maybe that's just because log n sounds like a long thing to
Log n is shorter than n, so it's actually like not bad.
It's
do.
very
Really?
fast.
Oh, it's shorter than, okay.
Log n is shorter than n.
Oh, okay, I guess I
because
can see why you
it's
use
it's how many times you would have to multiply 2 by itself to get to that number.
So that means the most efficient one out of all of them would be.
In terms of complexity, would be either of these,
Oh, okay.
which is actually kind of funny that sorted array is slower because you have to sort it.
Right. Wait, well, when it says efficient, does it mean out of complexity or does it mean out of, like, time?
Well, we don't know how much time it takes to do. We don't know how much time these take to do. So we have to do it only by complexity.
Right, oh.
So I would say we would do it by
Because we're
this.
calculating the time,
Oh,
not the complexity. So if we're calculating the time each one, I'm assuming he's just asking which one is the shortest. Which I would think is maybe VST question mark, because I also know, that seems like he's trying to teach us, oh yes, look, VSTs are good, don't. But I also don't know.
let's see, the time to do these, the problem is we don't know what n is, so
Yeah.
if it was a small n, then like
Oh, that's
logarithmic could be
true.
slower than
Yeah.
linear, just because of how the curves
Yeah, I guess that's
curve
fair.
and then pass each other.
Right.
Out of complexity, it would be one of these, and between these two, I would say it would be
Binary heap.
Yeah.
binary heap would, yeah, I would say probably, because this has 2 log n's, and this has 3 n's, and this only has 1 n.
Okay.
That was 3 in time to 100.
Huh? Yo, that's true, yeah, and since it's running 100 times, but that also depends on what n is. If n is way
Right.
bigger than 100, that doesn't really matter. So, we're gonna say binary heap.
Okay.
Hold on.
Which, if you think about it, makes sort of intuitive sense because we have a lot of maximum retrievals, and so a binary heap that can give us the maximum very quickly, and because it has a linear initialization is very useful. Questions? Cool. Next question. Last question. Oh, I want to make sure my phone's still recording,
I was
actually.
gonna ask about that. Do you have storage on your phone?
Oh, you didn't
Like,
plug it in.
Hours long
Huh?
video?
Did you?
No, I didn't plug it in, but it had a lot of battery. I'm just going to check if it's still on. Yeah, it's still there.
You might want to plug it in.
20% battery.
Yeah.
I think I have one more question.
True.
And it's over, I think, Trickle and Dijkstra's algorithm.
No, just crystals.
Just Trickle?
Dang.
I love Trickle. Trickle is my friend.
It finally made sense after your messy pie.
I know, it
No,
took
actually,
her like 2 minutes
100%.
to explain it, and I was like, oh, I get it now.
Yeah.
Okay. Okay. Execute Kruskal's algorithm on a given graph. Provide a list of edges in which algorithm processes them with a note whether it's added to MST or not. Why are there 4 of them?
Yeah,
What is MS?
They're all the same. Maybe he's doing the thing again where he's like,
It's the
the
number of
rest
steps.
of.
It's the number of steps you have to take to find the minimum spanning tree.
Yeah, but
Yeah.
why are there 4 of the
Because
same
there's only
graph?
4 steps.
Oh,
I can do this if you want.
I see.
I don't understand.
Sure, go for it.
Yeah.
Trickle,
Give me a-
yay.
You got
Let's
this.
go.
Believe
I
me.
wanna help you out.
Oh, yeah, oh, damn it. That was a good throw though, that was close.
3,
Okay,
Y'all
so
math people show us how
Discrete
to,
is so much fun, oh my
I
God.
don't
Discrete
like
is a lot
math,
of fun.
that
So the
sounds,
first-
it sounds horrible.
Discrete is
Uh,
great.
so first you should explain what the Kruskal algorithm does.
Kruskal algorithms
It's
finds
actually kind of fun.
Yeah, it defines the minimum spanning tree of a graph, given a set of edges that are sorted from least to most. So our set of edges is,
Oh, I know.
Guys,
I know.
please pay attention.
we have an edge from 1 to 2. We got 4 to 5, so this is the smallest edge. It has the least amount of weight, it's 1. So then the next one is 4 to 5 because it has a weight of 2. I'm reading way too big. That's
I mean, you could erase the random stuff that's on the board, it's also, like
Uh,
that Mr.
yeah.
Mime is kind of.
Also, I want to make sure the camera captures
Yeah.
it as
Oh,
well.
you know, that's so true.
Okay, let me write this smaller. So, our set of edges starts at 1 to 2.
So you're doing a sorted from minimum to maximum length, right?
Yep, so this is length 1. Then we have 4 to 5. Then we have, what is that?
Why is it the same thing over
One
multiple
more.
times?
Sorry, say again?
Why is it the same?
Because you can show each step
Yeah.
on each of the same, on each of the
Then
copies
the
of
next
graph.
one, the next largest one is, or the next smallest one is 2, 5, has a weight of 4. Then we have 3, 5, 1, 3, and
3, 4.
3, 4. Yes.
What is that, is that 4?
Yeah, it's a 4,
Yeah.
it looks, yeah,
Which one?
the 1 to
The
4, it
one.
looks a little
This?
wonky, that's a 4, yeah.
Yeah, that is 4. I draw my 4s weird. People
I-
tell me that all the time.
This is a collection of all of the edges sorted in order of their lengths or their weights, which is the number along the edge.
Yeah.
Yeah.
So we start with 1 to 2.
Mhm.
And we don't make a cycle with it, so we mark it down. So that's the first step. This one is included. The next step is to go to the next edge, which is 4 to 5. That doesn't create a cycle, so we'll put this one here. That doesn't create a cycle, so we'll put it in our minimum spanning tree. Then we have 1 to 4. In this step, it doesn't create a cycle, so we'll put it in our tree. So that gets included. Then we have 2 to 5. 2 to 5 creates a cycle, so we can't do that.
Yeah.
Because it would they would fill in that whole rectangle.
Right, and it would just make it a whole, yeah,
Yes,
yeah.
and because it's a strongly,
Oh,
because
so this is just to get, so that you can touch every node without making a cycle?
Yes,
That's
and
Okay,
correct.
well
That's the
then,
min-
okay, that makes sense.
And it also has the
Okay.
least weight, which is why it's called the minimum spanning tree.
Oh, I got you,
because it's an
okay.
undirected graph.
So that's what
any
Crystal
connection will
does.
be-
See,
Yeah.
that explains it so
That's
much better
what-
than anything
Right?
anyone's ever said.
Yes.
Okay, great.
Yeah, Vermesi is a wonderful teacher.
Okay.
Yeah, if you have a
Agreed.
chance to have her for anything,
I'll
she's
see.
great.
I think she's the only one that teaches discrete.
Oh, yeah, because then
so-
3 to 5 would finish it, I think,
Yeah,
right?
see,
Is
3 to
that what it
5 is, well, let's see,
is?
what's
Not
hard?
to spoil.
Not,
the
yeah,
answer.
spoiler alert, jeez.
Yeah, spoiler alert.
So then, yeah, 3 to 5 does not create a cycle, so we include it.
And that's the whole thing.
Yeah, that's the whole thing, because
Because
everything else
everything's fine.
creates a cycle.
And even though they're
Yay.
visually crossing, that's fine. It doesn't matter.
Yeah, because you could also rewrite the tree as like,
You could just move 3 over
1,
to the right and then it would still
I'm
go.
just gonna, okay, there's no way I can translate that out here. It's like,
Goes into
this.
4 and then
If
to 5
you
and
imagined
5
they were
goes
like
to 3.
strings, you could just move the 3 to 5 string
Yeah.
outside, so it's
Yep.
a house with a little bubble on the outside.
Exactly.
Yeah.
Perfect. Awesome. Thank you for
Thanks,
demonstrating.
We
so
got a
much
yes
fun.
teacher.
Yeah.
We did it.
Perfect. That is a very good explanation of Kruskal's algorithm.
Thank you.
Cool. And I guess there's no questions about disjoint subsets or anything on here, so we can go over those if you want or not.
Well, I mean, he's gonna probably put questions about something that wasn't on here.
Do you want me to explain
Yeah.
disjoint
We,
subsets?
we
Yeah,
won't,
let's
we
do
won't
that.
know what it is until it happens, so. I think we'll be prepared.
Okay, so this is still related to Kruskal's algorithm, and it is an optimization technique to reduce how long it takes to find a cycle within a graph. So normally, you could represent it as a table that's like, hey, what quote-unquote color is each, and basically anything that's already connected will have the same color. And so you can say, oh, if this is a different color, then make it the same color and spread the color to all of the connected nodes that you've just connected. So if you connect two trees. So
Bless you.
if that still streams everything properly, right?
I mean, the camera should still be on regardless, so you should be fine.
Right, so the camera, yeah, for this part, it's gonna be the camera, I'm not gonna be doing anything on the screen. Yeah, so, yeah, okay, so,
Let's do a cookie.
Okay, so, this is our graph. We've got edges here, 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 and we want to make this a minimum spanning tree. I mean, okay, sure, this graph is already a minimum spanning tree. We'll add some extra edges to make it not obviously one.
Beautiful.
So what we're going to do is I'm going to just recreate that minimum spanning tree I started with. So let's say we start with this edge. We'll put this edge in, and then this edge, and then this edge, and then this edge. And now we want to connect these two into one tree, because right now they are two separate trees. And what I would have to do is say, okay, add this, but now, okay, let me go back. What I would do is, now I would have, say, a red tree and a blue tree to say, okay, cool, these are all good. Now what I can do is I can say, if I connect this as part of our minimum spanning tree, then I have to choose one of these. I'm going to say red because whatever, red ink. And now I have to say, now this is also part of the red tree, but for each of the nodes, I have to, or I guess, is it the edges? I think it would be, the edge. For each edge, you define a color of the edge.
Oh, yeah.
So this is a red edge, this is a red edge, this was a blue edge,
But now it's red.
and this one was blue. And now I want this one to be red, which means I need to spread the color to all connected edges,
Oh, okay.
which means I need to spread it to all edges connected to this one, which means now these are red, and this is red. But that means I have to, if I just keep a list of all the colors of all the edges, then I have to go through all of them to find all of them that were blue and turn them red. But I have to look through all of the edges, not just the ones that are blue.
Why? What's the point of doing that?
So if there's also a green tree down here, now if I just have it stored as a list of like, oh, this one's red, this one's green, this one's red, this one's red, this one's blue, this one's blue, this one's green, because this one's also green. Then if I want to turn all the blue ones into red ones, I have to go through this entire list and say, are you blue, are you blue, are you blue, you're blue, turn it red. Are you blue, turn it red, right? But with disjoint subsets, instead of storing just an array of the color of each, and the point of this is that it finds a cycle, so if I connected this, I can say, oh, red and red, oh, it's a cycle.
Oh, okay.
That's why you can quickly determine if something is a cycle or not. So the way to make this so you don't have to scan through all of them is instead to store them as like, okay, we have edge 1, edge 2, edge 3, edge 4, edge 5, and we can say, okay, this one's red, this one's green, this one's blue, this one's yellow, this one's magenta, as a beginning state. And then when we add an edge to the tree, we can say, okay, we want this one to be red, so we're actually going to just make a linked list here that says, okay, 2 is also red, and then this one is going to point to 1. And now what it means, and then if we add this one, as well, we would say, okay, it's now a linked list that goes from 1 to 2 to 4, and 4 also points up to 1. And now what it means is that if we then add something to red by adding it to edge 4, we can say, okay, instead of having to go through all of the edges, we can just go directly to the red ones and change all of the red ones. So say we wanted to make them all magenta, we could just say, okay, make this magenta, and then all of these are magenta, and this one then points there, instead of having to go through and hit the blue one and any other colors that are already there. So this is called disjoint subsets because it's basically an array of linked lists.
Cool.
Neat. Questions?
You would think there's only so many ways you can arrange a linked list.
Yeah.
Crazy.
You'd be surprised.
Linked list of arrays of linked lists of arrays of linked lists.
I mean, there's a reason why that, like, those types of videos that show sorting algorithms with all those beeps and bloops.
I love those.
Yeah, there's gotta be some.
ADHD glue
All right.
traps.
Any other topics anybody wants to review? Wants a refresher, an explanation, recap?
Why?
Yes, why do we have to do this?
Why?
Why?
Why are we doing this to ourselves?
Why do we choose this career path?
Why am I metaphorically hitting myself?
Knowing the
by taking
pain,
classes
the
I didn't
pain
have?
that was, wait, that's not what,
It's not really.
That's
a question.
why.
Has anyone looked at the water retention assignment?
Nope.
I have not.
I have.
I have started.
I have not done.
Allegedly, there is a solution to it online.
Yes.
I have not found a
Justin
solution.
has said that it is a common problem so that you can find the answers online. If I get the solution from him,
Please pass it
I
this
will
way.
distribute it.
Cool. All right, well, we're gonna end the recording and pack it up there then.
And my